All right, hello everybody, and welcome to the stream. My name is Nick Larson. Today is May 23rd, 2019, and it's about 12:30 in the afternoon. Um, been a good day. I'm enjoying. This has been a good week. My time schedule got thrown off a good bit last week due to some unexpected craziness, but things have sort of come back to normal. We had a little baseball game last night for my son. We had some gymnastics, like graduation thing this morning for my daughter. And yeah, things are just sort of getting back to normal, which is kind of nice. So yesterday we were working on decision trees. And that is actually what we're going to... Oop, I gotta change that. 44. Save, update that information. That is actually what we're going to continue working on today. We, yesterday, made a single decision tree. Hooray. And this time, what we want to do is we want to implement the XGBoost wrapper that goes around this that does all of the magic. In some research that I did yesterday, and a little bit this morning, as to how it combines the values from the leaves of these trees, what we identified is that it takes all of the leaf values of the trees, adds them together, and then it just passes them through a logistic function. On the back side of that, you end up with a probability, and that is the probability that is used to then pass on later on to whatever else it is that you're going to do. So that's all we need to do. Basically, we have a way to make a tree. Now what we need to do is we need to write an XGBoost. Just so y'all are aware what XGBoost is. It's a tool. XGBoost. It's a tool written by some people that is basically like a library for doing this, and they have the model that gets trained, and then we spit out the model, and that's what ends up being dumped into this right here. And this is the model that gets dumped out. Again, you don't need to worry about what these features are. It doesn't really matter, just that they're features. And then this is the branching operation. So if this is true, then you go to this index. Index is the first number before the colon. If it's false, then you go to the second one, and the 6 just happens to be right here. It's another branch. It looks at a different feature, compares it to another value, does some other magic. These things, the gain and the cover, are really just some reporting metrics that tell you how much, I want to say it's Guinea entropy, was gained by making this selection. And then the cover tells you roughly how many of the training samples are still in the tree at this node. So all of the other samples have been handled somewhere else. This is how many are left in this. And the reason it comes out as like a partial number is, frankly, I don't really know. That's my answer. I don't know the answer. I just don't know. Anyway, missing in this case always goes to the same thing that yes goes to, and the reason for that is we replace all missing values with the value 0. So this always ends up being yes, because the right side of this inequality is always going to be a positive value for the trees that we're using here. If it were true that one of these was negative and we substituted it with 0, then this might end up going the other way. But for now, it doesn't really matter. You just replace missing with 0, and then you go to whatever direction, yes or no. So we don't actually worry about the missing parameter either. What we did, we took a single tree, boom, all the way down to here, in between booster 0 and booster 1, and we then populated a decision tree based off of that. We also wrote an evaluation function that will evaluate this decision tree, and we wrote some tests to show that we are actually generating the correct tree, and to show that the value that gets popped out is the value that we expect. Now what we're going to do, write the XGBoost wrapper, calculate the logistic score for a bunch of samples, and then we're going to, and those samples are in here, but I can't click on that. until I modify this, which I have to do off screen to get rid of the actual feature names. And then when I'm done with that, then I will go ahead and test it up, and we'll be able to compare it against what it, you know, what the real XGBoost tool came up with, and then we'll know how close we are. And that's the plan for today. And then after that, we're going to spend a little bit of time doing some benchmarking to see how long it takes to actually run all this crap. And we need it to run for roughly 10,000 jobs in roughly 45 or 50 milliseconds, like at an absolute maximum, for like the worst case scenario. So we'll see how we do. And let's go ahead and get started. So let's write this XGBoost wrapper. Datasets fast.modeling.test. Okay, we'll keep these open. And in here, we'll say XGBoost. XGBoost. I don't know. Wrapper. I'm just going to call it a wrapper for now. We can change it later. And up here, we want all of this crap. Okay. Link. Actually, I'm going to keep that in here. All right. Public class XGBoost wrapper. All right, what should this have? This should have basically a bunch of trees. So private decision tree array trees. Then we also want the same sort of method that we used for the decision trees. We want to make private XGBoost wrapper decision trees this dot trees equals trees, and then we want the same sort of idea where we want a create function, public static XGBoost. I should just call it XGBoost. It'll make more sense in the code that it'll eventually go into. XGBoost create model from a string trees. All right, this is here in the decision tree test, and we can go ahead and just start whipping this together. Like, yeah, like this. Test XGBoost create, and this is going to be XGBoost.create, and instead of an example decision tree, we instead want to load up this entire file from datasets. So let's just go ahead and add, create, there we go. Throw new, not implemented, just so you'll actually compile. We have a create, we don't want to do that. And what we want to call this is model. And then as far as the test, to do, figure out how to see if it's the same, which is actually going to be pretty simple. We're going to follow this same pattern of creating these individual trees. The only difference is instead of doing one tree, well, We're just going to check each tree to make sure each tree. So basically we're going to run this for each tree. And then we'll know we've done it correctly. Mostly? Sure. Alright, the data sets. How did I load the data sets? Let's go to the find data sets. File name. Oh, literally, I just have this. Yeah, well, you gotta do what you gotta do. Okay. And for this, we want var file name datasets, and not Lima. We want datasets dot. Should probably stick all of this stuff in the same folder. So let's call this xgboost. I have to drag this off screen. Hold on. Move. Okay. There we go. And then basically want to copy xgboost slash model xgboost trees.txt, and then we want to say var tree string trees string equals file using system.io. We want to say file dot read all text file name. There we go. And then we want to pass in here trees string. Okay, great. That will allow us to fire this up and create it. So really what I want to do now is get to the point where we actually create the entire model. And then I want to see if we can get to the point where it actually loads it up and does it. And then we'll fill out this part. Let's rename this from XGBoost wrapper to rename XGBoost. All right, trees, XGBoost, decision tree, trees, not implemented. All right. For this, what we want to do is basically split on all of them. And the way that we are going to do that is we are going to say okay, private static read only regex tree split equals new regex. In the file, we see that this line represents a split, and we want everything. We want everything above it and below it, and there is a blank line at the end of this. Let's just keep that in mind. Okay. So what we want is start of line booster open brackets /d plus close brackets, and this is a regex, and we want regex options dot compiled, whatever, and one more, regex options dot multiline. We need to do multiline. Oh, and I need to put the end of line trigger here. And what this should do is it should split every time it sees this, and we should get individual trees to pop out. That's the plan. So let's do var tree strings equals tree split dot split trees, and then we want to say var trees equals trees string. Okay, how about all trees? All trees. And then we have trees equals tree strings. I'm having a hard time typing. Dot select decision tree dot create dot to array, and then we want var model equals new xg boost of trees, and then we want to return model. Okay. There is this thing where we do a split, and I want to ignore all of the ones. So we're going to say we need to basically ignore. I'm expecting this to fail. To do check if we need to ignore empty strings. And then the last thing is that very last one down at the bottom has a blank line. In fact, let's go ahead and take care of that now. If there is a blank line, we need to filter out the blank lines. So in the decision tree create, we take the definition, we split it on new lines, and then we need to say dot where not string dot is null or white space m. So this will ignore the lines that are null or white space, and then it will only parse the other lines. So that extra empty line at the end shouldn't matter anymore. And we have that in this test now, so we can go ahead and fire that off just to make sure. Run this test. Okay, and that passed. All right, we're good to go on that. So now I have no idea what these are going to look like. I guess we could just take a look. Let's just do a little breakpoint right here, and let's go see if it works. Decision tree. Right here. Debug it. Wow, that is loading some stuff, isn't it? My goodness. Fast. Okay, culture of development. Fast. Could not find the file. Let's go take a look. Actually, let's go take a look here. Culture of development. Fast. datasets, XG boost, model XBG. Goodness me. Have I screwed this up? Fast datasets. Did I type this in wrong? No. Did I type this in wrong? XBG? Oh, I did. XBG. Okay, stop. Debug. Yay! Tree strings. Alright, the first one is empty, so we do need to filter out empty strings. Another thing we probably want to filter out is new lines. I want to say it's going to be like that. Okay. And then we want to say dot where not string dot is null or is null or white space m. And let's try that one again. Why is Newtonsoft in here? Feel like it's busted. How about we just stop this and we go to the test and we debug the test. Okay. That definitely got rid of the new lines. That's not what I wanted. Okay, let's go to watch. You can just delete that. We want tree strings dot first. I can't do extension functions. 0. What on earth is going on here? What is happening? Tree strings. Okay. Okay. 1. Copy value. Give me a new file. Paste it here. Okay, ends in a new line, and I'm totally fine with it ending in a new line. Because we just handled that. Maybe one thing that we do is we just trim it. No, I'm not that concerned about it. Okay, I think this works. So we ought to just be able to play. Close that. Oh, well, no, we know this isn't going to work. Oh, yeah, no, we did add this. Ah! Okay, let's just see if it works all the way through. Okay, it passed. Great. Okay, now what we want to do is make sure that it actually spits out the right thing. So that is basically going to be me calling this for each of the trees. Let's write a little helper function called private void ensure correctness of decision tree. Decision tree dt. Okay. Ensure correctness of decision tree. Great. And then we should just be able to got to get all of the trees out of the model. I guess we could just make it public. Sure. No. Public decision tree array trees. Okay. Now we can get at it. For each var tree in model.trees ensure correctness of decision tree. All right, run that test. Failed. Node could not be found. Okay. I need this to give me hell. All right. My decision tree. Oh, example decision tree. Oh. Yep, that's much harder. Without replicating the logic. I feel pretty confident that it, you know what, I'm just going to leave it to do in here. To do ensure correctness of each tree. Hey, Codebase Alpha, thanks so much for the raid, and welcome everybody if you're just stopping by. That's awesome. I hope you had a great stream. I hope your chat bot, or I don't know, were you working on your chat bot? That thing was pretty cool. Big shout out for Codebase Alpha. There we go. I guess if y'all are coming from there. But yeah, thank you anyway. I really appreciate that. And like I said, I hope everything was going pretty good for you today. To do ensure the correctness of each tree. Dun dun dun. As hard as that's going to be. And then I'm going to get rid of this because this only caused problems and confusion. Okay. Much better stream. Awesome. Glad to hear that. All right, what we are working on is I was given a model by my data scientist. It is developed in R using a library called XGBoost. I am taking this XGBoost model and I am trying to convert it over to C sharp. The implementation in R for like running through the model and calculating, the probability that this event occurs is extremely slow. Like slower to calculate a single match between a job and a user than we can allow. So my job really is to like take this model and then speed it up by a factor of about 10,000. Right, yeah, data science. I'm a data engineer where I work, so I don't do the science part of it. But when it's time for the models to go to production, it's my job to make sure that they scale up and work at the speed they need to work at. So that's what we're doing right now. Yeah, I don't always get to work on stream, but today and this week just happens to line up really well. There's only one thing that I have to do off stream, which is going to take me about 2 minutes, which is getting rid of the names of all of the features of this, because I can't actually show you the names of the features. Yeah, 10,000x is a pretty big speed up. We're going from something that was taking about 1/10 of a second, and instead I need to do about 10,000 jobs. Well, it was taking anywhere between like 1/10 and 1/100th of a second. So anywhere between like 10 milliseconds and 100 milliseconds to do a single match. And I need to do 10,000 matches in 45 to 50 milliseconds. So yeah, a lot of work to do here. And right now all we're doing is we have the model printed out, and I need to instantiate the model, which I have just finished doing. And now I need to actually run some tests against this, run some examples through it, make sure that the values that are being spit out are the correct values. And once I get done verifying that, then we are going to write up a little benchmark to see how fast we are at the moment and then where we need to get to. And there's a lot of tricks that we can do around this, which is going to be the fun part. But yeah, this is sort of where we're at right now. What do I need to do? I need to write the evaluation function. Public double evaluate. Or I guess we called it, yeah, just I'm just going to say evaluate. Evaluate probability. Probability. And then we're going to pass in whatever needs to go to this, which is a float of doubles, an array of doubles. Instance. And I probably want to even make this something more like that, but I'm not going to worry about that for now. Okay, so for a single instance, what I want to do is I want to say var sum equals trees dot select m. I can just say, yeah, m dot evaluate of instance dot sum. And in fact, I don't even need that select. I can just call this dot sum. Okay. And then I need to pass this through a private logit double logit of a double value return one double divided by one double minus math.exp of value. Negative value? Let's just logistic function. This is what we're implementing. And it is negative. Yeah, I got to do a negative here. Negative value. And then we just var result equals logit of sum, return result. Okay, and that's all you need to evaluate this whole thing. So the amount of code that goes into like doing an evaluation is ridiculously small. If we take a look at the decision tree, once it's instantiated, this is the entire evaluation function. You just like go down the tree, find the leaf node that has the value, return the value. Then to do the full boosting model, you literally just take each of those trees, sum up the results, pass it through a logistic function, it spits out a probability of success. And that's it. So this model was learned. It's really easy to actually implement. This stuff, I don't think right here we're going to do any faster, and it's also not... Well, there are ways we could do this faster. We'll worry about that later. Eventually what's going to happen is we're going to pass a single user in for a lot of jobs, and I am probably going to do an excessive amount of pre-calculation to not have to worry about the job information and instead only worry about the user information. But we'll get there when we get there. So that is that. I need to do some stuff off screen for a minute to get rid of some feature names which I am not allowed to share, and then after that I will be able to share it again. So we're just going to go into full screen mode here. Yay! Hello! If you have any questions about anything, by all means drop a line. I'm just going to be doing this on the side. It's literally just going to take me a few minutes to get these names out of here, and then we can get right back to it. So if you have any questions, like I said, just feel free to drop me a line. Happy to answer questions about anything, any kind of code, any stuff that I work on, anything like that. Whatever it is that you're working on. Be interested to hear about that as well. Go here. I want to go here. I want to go here. And here. I want to set this as my working directory. I want to say tidyverse. I want to say features equals read CSV final features.txt. Okay. That is not what I wanted. I need to modify this. Feature. Save. This one. Okay. Close that. Close it. Features. Okay, now that's what I wanted it to be. Let's see. Oh, what's your favorite drink? I now need to open this in. Oh, that one's good actually. Okay. That is test cases. Let's read CSV. I am reading XG boost test cases. Great. Now I need to take features, mute features equals mutate feature index Crap. Test cases feature index equals row num -1. Let's take a look at features. Okay, great. And then I need test cases, inner join, test features, inner join, test cases by equals feature. What is going on here? Well, I have managed to break this, which is awesome, because I didn't know that was even possible. Oh, well, that's awesome. Stop. Yep, just kill it. Wow, I have managed to completely destroy this. Oh, you know why? That is a lot of features. I'm just gonna have to kill this whole thing. Shouldn't. Okay, there we go. Fast, datasets, XGBoost, set as working directory. Okay. Features equals read CSV mutate feature index equals row number -1. Okay. Test cases equals read CSV XGBoost test cases. Now what I want is test now what I want is test cases final or no features equals test cases inner join features by equals final features. Okay. Interestingly, there were some features that got lost. That's crazy. And then what I want to say is mutate feature equals feature index and drop feature index. How do I remove a column in R? Tidyverse remove column. Oh, select -1. That's right. Minus feature index. Okay, test cases. Data ID feature value. Data ID feature value. Okay. Yep. Okay. Let's save this. Rate CSV XGBoost test cases no features. No feature names .txt. Error. Error. Oh yeah, you gotta actually tell it what to write. Test cases no features. There we go. And guess what? It's a much smaller file too, because almost all of the data was in the names of the features. Okay, great. This is just going to take one more second for me to get rid of the files that I am not allowed to show you. Delete. Delete. And then we can pop this back. Okay. All right, back to the real stuff. Cool. Okay, so let's take a look at what we just did, what I just did behind the scenes that you weren't allowed to see. Test cases, no features. All right, now what we have is a feature index. This represents the number that is next to the F right here. So we don't actually care what the feature names are. They don't really matter. What we're going to do is we're going to create an array for each one of these test cases. So we're going to look at this. We're going to create an array that has, I don't know, 500 or some odd, 800 or some odd. A lot of features, basically. I want to say the maximum number is like 850 or something. So that's essentially what we're going to do. We're just going to create an array of 1,000 doubles, and we're going to populate these values into each of those. And what these values represent, not super clear, but it doesn't really matter because you don't need to know what they are in order for the model to work. So let's go ahead and populate this. This is a decision tree test. Now we want to do a decision tree evaluate, but not decision tree. We want an XGBoost evaluate. Boom. Test XGBoost. Evaluate. And that's how you create your model. And model dot evaluate. XGBoost doesn't have an evaluate. I must have misspelled it. Oh, evaluate probability. Sure. Guess I was being explicit there. Probability. All right, and we're not going to use test values for this. Instead, we're going to load up this other file. That's the trees. This is the test cases. Give me the file name. Rename. Control A. Control C. All right, we have the entire file thing up. We want var samples string equals file dot read all. I'm just going to say read all lines to save me from having to do that later. And this one's going to be file name 2 because, you know, we're good at naming around here. File name 2. And now for each of the samples, we're going to say var samples equals new dictionary of string to double array. And then we're going to say, why is that giving me trouble? Because I don't have it included. Using system.collections.generic. You should be happy now. Directory? Oh, it's not directory. Dictionary. Okay. For each var line in samples string var parts equals line dot split on commas, right? So we have commas and then there's 3 values. We're going to leave the first one as a string. The second one we're going to convert to an integer. The third one is going to be a double. Okay, so var, and this is one part where like I really wish they would come up with some better syntax for this. I don't know if there's really better syntax per se that's like easy, but like I have an array of 3 parts and I want it to come out and just do the same thing to all 3 parts without like instantiating something each time. I have 3 parts. I want to say the sample equals parts 0 var feature index equals int.parse parts 1 and var value equals double.parse parts 2. Then I want to say if samples.contains key, or rather if it doesn't, dot contains key, let's just do it if samples.contains key sample, then we can just say sample samples of sample. Now we have a double. Then I can say feature index equals value. Otherwise, I need to say samples dot add new sample new double array 1000, and then I can do this. So really I do want to do it like I had it. If not, because then we can just do this. Okay, so now what I've done is populate all of my samples. And now for each sample, oh, what is the, oh, that's what it is. Okay, I gotta get one more thing off screen. No, I don't. No, I don't. Yes, I do. Yes, I do. Okay. This will just take a moment. Okay, give me these. Go back to this. Restore. Okay. The fast datasets XGBoost. Show set as go to set as. All right, one more time now. Features equals read CSV. Oh. Okay. Equals read CSV. And we're reading final features. And we are mutate to say feature index equals row number -1. And there's one more thing that I want to do. Want to read it in test cases equals read CSV XGBoost test cases. And now I want to I think that's just that. Yep. Now I want to say test. Now I want to say I want to say test cases anti-join features by equals feature. Oh, that's interesting. That is super interesting. I don't know what to do about that. Okay. Features. Filter grepl of feature grepl. It takes in a pattern first. Okay. Let's just put in WordPress and then feature. Should tag percent. just don't know. Okay, how about we do a distinct feature view. XGBoost prob. That's the one that I want. Okay. Now I'm going to add this to this file. And it is 841. Okay, now I need test cases 2 equals test cases inner join with features by equals feature mutate feature equals feature index select minus feature index. Test cases 2 looks a lot like what I want it to look like now. Great. Now I want to say test cases 2 write CSV to XGBoost. There we go. Okay, let's try this one more time. I now have a magic value for each one of these, which is 841. Const int probability feature index equals 841. Now what I want to say is for each var sample in samples I want to evaluate the probability. Probability equals model.evaluate probability. Of sample.value. And then this needs to be sample, well, let's just have it be var expected equals sample.value of probability feature index. Actual. Okay, so asserting equal on some doubles, probably not the best idea. Assert dot in range. This is probably the right way to go. Let's just see what happens. Because we're going to know if we're even like on the right track or not very quickly here. Based on whether or not this actually loads correctly. I want to step through this. I want to take a look at this one time, just to make sure when we get here that I can evaluate it myself to make sure, looking at these features, which I think we need to reload. Oh, that's a problem. Delete. Okay. Looking at these, we should be able to go through and verify that these values are the correct values for the sample given to us. And that's really the plan. We just want to take a look at that real fast to make sure that it's doing what we expect it to do. How do we do that? We just debug it. I'm going to guess this line is an empty line. Oh. Duh. Stop. Let's skip one. Using system.link. Okay. Probably need a check. Okay, no, okay, that took care of everything. Okay, so what we want to do is we want to take a look at samples right here. Let's just go here and clear these out. Remove, remove, add in. We want samples. Can you do it like that? Does that work? No. That'd be way too easy. Give me that. I don't think that actually copied it. Oh wait, we can just do it like this. Hey, Codephobia, thanks for the follow. Hey, all right. Ace Flames here, thanks for the follow. Really appreciate that. What we're working on, I don't know how long you've been around here, but what we're working on is basically taking a model that was built in R, converting it over to C#, and right now we're testing to make sure that the values that come out on the back end are the values that we expect. And then after that, we're going to write up a little benchmark for it, and then we're just moving straight into performance work because we have to get this thing to be a whole lot faster than it is in R. And hopefully it goes pretty fast. I have no doubt in my mind that a lot of the pain in R is that it's like taking it and then sending it to like a C API, which then sends it back to R, which then sends it back to a C API, then goes back to R, and it's all that conversion back and forth that's causing the majority of the slowness. And so I'm hoping this will just like be a lot faster out of the gate, but you know, we'll see what happens. Okay, for this one, are these in order? All right, for 1, we have a value of 0. For 0, we have a value of 1. For 2, we have a value of 1. For 3, we have a value of 0. And then up here, we go up to the top. For 4, 19491, 194915. It's close enough for me. Oh, look, there we go. Okay, 757, 271, 418. All right, I'm pretty convinced right now that this is actually working correctly. So we saw the ones at the beginning and we saw the ones at the end. So I feel pretty good about that. There is a lot of mathematical imprecision that's about to happen, and I have no doubt that when I press the continue button, this is going to bomb on like the very first try. What's my actual? Well, that's interesting. You can't have a negative. You cannot have expected 0. Great. Oh, frustrating. Let's go look for 841. Okay. Well, you can't have a negative probability. That's an impossible thing. So we have a little bit of work to do. And then the second part is there needs to be some 841s in here. Hey, thank you, Ganesh, for the follow. I really appreciate that. I hope everything's going well for you. It's the evening time there, I believe, pretty late. Let's search for 841. Comma. Ooh, not good. No results. Why did I not get any 841s? Why did I not get any 841s? All right, well, one more time I have to do this conversion one more time. Recycle bin. Restore. Go to R. I wonder if it's like trimming that's the issue. XG boost probability. Oh, I'm glad to hear that. .net. Nope. You know what? I think it's probably time for like a 30-second break. Keep looking at the same thing over and over. The same thing is going through my head. I think it's probably time for a very, very, very short break. Set this as the working directory. Tidyverse. Features equals read CSV. Final features. Oops. Mutate. Feature index equals row number. It's 1. Okay. XG boost test cases equals read CSV XG boost test cases. Oh, yeah, I don't know. Okay, now what I want to do is say XG, I want to say test cases group by, we're going to group by the feature. count filter feature equals XGBoost prob 5,000. So there's 5,000 samples in here. Interesting. I want to say that if we do not count, I just want to say distinct sample? What is it called? Data ID. In row. Okay, so there are 5,000 and there are 5,000 outputs. So test cases 2. You know what happened? I might have had this open and it might have just saved the file. Test cases 2 equals test cases inner join features by equals feature count. Now we're just going to do this all over again. Okay, I got all 5,000 of them in there. Now we're going to say feature equals. Oh, you know what we should do? We should actually just filter. Wait, I might not even need to do this. Features filter feature equals XGBoost prob. Oh, it's 840. Oh, why would that happen? One of these is poorly formed? Or one of them at a comma? Okay, so it's 840. Who knows why I decided to do that? I want 840. All right, let's try this one more time, but we're going to stop it here instead because we know it's going to fail. Okay, the expected for this one, and I guess we can go ahead and sort of figure that out. Can say feature, no, not features, test cases filter feature equals that. Arrange by data ID so we can find it. View. All right, what is my sample? 242585. Oh my. It's going to be near the bottom. 242585. 242585. 242-585-192-985. All right, and 3 point. Nope, expected. 0.3708. Okay, so good. All right, we got the correct expected value out. Now the actual value, that's causing a lot of problems. So evaluate probability. I'm pretty sure I've done this before. Whoa, 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 whoa. Oh, shit. Saved it. Just in time. Okay. Come on. EXP. Didn't expect that. Math.exp. I don't want anything to do with alglib. 1 plus? Oh, it's 1 plus. There we go. All right, let's try that one more time. I have a better feeling about this, but still not great. Stop. Oh, those are close. Okay, these are really close. 3708135. And that's a 134, but it would round up. So that's 1, 2, 3, 4, 5, 6, 7 decimal places. I feel good about that. Let's do within 7 decimal places. Okay, stop. Let's do 6 decimal places. Assert.inRange. What we want is expected times 1 e negative 0.6. Oh, that's the actual. That's the low, not times, plus, and expected, yeah, so low would be minus, and then expected plus 1 E06. Okay, and hopefully this is correct for all 5,000 of the samples. Hopefully this is correct for all 5,000 of the samples. I don't want that. Debug output. Okay, just run it. Oh, it passed. All right. Okay, great. Okay, so we are generating the same values as the R tool is generating, which is great. Now let's put in a little benchmark harness. so that we can make sure that this is fast enough. If we were doing 5,000 right here, that's actually kind of enough to get a rough estimate. So let's do var timer equals stopwatch. Yep, using system.diagnostics. Okay. Stopwatch dot start new timer dot stop. And really what I want to do is do this twice. Int I equals 0. There's 5,000 samples in here. I just want to basically do these samples 2 times over. And that will estimate roughly 10,000 jobs going through this thing. Get an idea about how close it is. Output.writeLine. Time taken for 10,000. Well, let's just be really explicit about putting in the correct number here. Time taken for I times samples.count run evaluations plus timer.elapsed milliseconds. I don't want elapsed milliseconds. I want elapsed dot total milliseconds. The difference between just saying elapsed milliseconds and total milliseconds is this is a double. Hey, Code Rush, thank you so much for the raid, man. I really appreciate it. I hope you had a good stream today. Are you still working on? I think the last time I watched you earlier this week, you were working on some updates to your actual Chrome for your stream. Did I have that right? And if I did, I hope it's going well for you. Yeah, the difference between elapsed milliseconds and timer.elapsed.total milliseconds is that this one is actually a double, whereas the other one is just a long, and it doesn't give you partial milliseconds. This one will give you partial milliseconds based on the number of ticks that have elapsed, not just some raw count. Okay, so this should actually tell us how long it's taking. He does cool dev stuff like this. Let's check this out. Nice.
Oh, spectacular miss.
Yeah, that's cool. What is that done with? Man, that's awesome. Yeah. No, that was serious. That was amazing. Was that using like Three.js or is it just like raw him doing that? Where's the animation come from? That was really incredible. All right, let's give this a go. Run. I don't know if it's compiling it in like debug mode. Ooh. Surly Dev, thank you so much for the follow. I really appreciate that. Okay, so what we saw here is that 10,000 evaluations is taking about 1.4 seconds, 1.5 seconds. Okay, so this is faster. Hey, Hugo Doll, what's up? The dice is 3JS, but the extras are Helm. That's awesome. It's going great. I get to work on work this week on stream here, so I'm having a lot of fun with that. Basically, I was given a model, boosted decision trees, basically spit out to me, and now I have to convert it from being like in an R package to being in something that runs in C sharp, so that we can run it in production on our side. Uh, right now, we just finished getting the model loaded up. We just finished getting it in here, and we got a really quick timer put on 10,000 evaluations, and it takes about 1.5 seconds for 10,000 evaluations, and we have to get this down to about 45 milliseconds, 45 to 50 milliseconds. So if we're at 1,482 milliseconds, 482. Oh, wait. And we need this to be... How many times do we have to divide this by 10? That's the real question. Divide by 10? 148. Divide... Okay, so we need like a what? A 20x speed up at this point. That's not... That's not the end of the world. Am I making that up? I am making that up, aren't I? We need a 30x speed up. Let's just say 1500 divided by 30. All right, so we only need a 30x speed up, whereas initially we were going to need a like 10,000x speed up from the way that R was doing it. R was taking an excessive amount of time. Yeah, only need 30x. I honestly don't think 30x is going to be like the end of the world to get here. This is done really, really poorly the way I have it, and with a couple of minor changes, I would expect for us to really be able to cut this down to the correct ballpark. But, you know, we'll see. Okay, so basically what we have done is we have built a model in C Sharp that loads up the model that was outputted from R, and we have verified the correctness of the values that it's generating. Now what we need to do is get in here and grind away on improving it. Right now our nodes are like actual nodes, and we store them in an array. And this has the problem of being sort of like a jagged array, so to speak. One thing that we could do is, instead of having this be a class, we can just literally make this a struct, and I would not be surprised if this immediately got faster. The difference between having an array of classes and an array of structs in C Sharp is that with an array of structs, usually the array itself will allocate enough space to hold the entire struct, whereas with a class, it's creating references. And so there's an additional lookup. So hopefully just doing this like really stupid minor thing is going to have like a noticeable impact. And we're going to see. It's also possible that I am compiling in debug mode and not release mode. Okay, so that had an impact. So not, you know, not as large as I was hoping for it to have, but it still made a difference. Hey, it's Doozy. Thank you so much for the follow. I really appreciate that. Let's see. There are some other things that we can try. What else would we like to try? We would like to try the fastest. Well, first, yeah, let's just make sure that we're actually compiling this in release mode. How can I even tell that? Like, literally don't know how to do that. All right, Ganesh, I'll see you on Monday, man. Thanks for stopping by. I appreciate it. I think one thing that we can do is we can, like, just literally tell it to build and release. .NET build config. How do you tell the config? -C. release. Let's go take a look. Bin, debug, release. All right, rebuild everything and release. So we were definitely running in debug, hopefully now running in release. How do I, somewhere, I think it's in this to do maybe? Yeah, right here, .NET test, filter this. .NET test, not here. CD space fast.modeling.test. And then I want this, only fully qualified name. I want to be fast.modeling.test. Decision tree test, probably. Decision tree test dot this one, test xg boost evaluate. Oh crap, I want to say it prints out a file. It's supposed to write out a file. Where? When I call this output right here, right line, is it in object release? What would it be calling the file name? Nope, don't do that to me. You know better than that. It's this thing right here. Test base. Dot test output. I have no idea where it's actually writing this. I would expect... Oh, I'm in modeling. I need to be in test. No wonder. Bin, release. No? Did it go to debug? What's today? The 23rd? And is it 1811? Oh man, it's still running the debug. Okay. I think I need a -c release. Okay, that time it spit it out into a different place because it didn't show up here. Just kidding. Can I delete these? Now, can I run that one more time? Does anybody know how to get... Oh, there they go. Okay, time taken. All right, so yeah, running in release mode down to 478 milliseconds. Now we only need a factor of 10 speed up. Okay, this is good. We're doing great. I should make this a little more explicit. We're like almost on point here. Should make this just a little bit more explicit that this is actually milliseconds. Milliseconds. Total milliseconds. I feel confident that that's actually total milliseconds. Okay. And yeah, we only need to increase by a factor of 10. So there is probably a lot of speed gain to be had here by thinking about these trees a little differently. So In a decision tree, you're making a decision. That's an if-then statement. String interpolation and concatenation on the same line. Oh, yeah, fair enough. You make a solid point. It's about whatever's in my head at the moment. We go back, we clean things up later. The first iteration is always a rough draft. Um, all right, so for a decision tree, you are making a decision, which is a literal if-then statement. But the way that I implemented it, I don't believe that we're actually creating a branch instruction. The way that it is implemented for a decision tree is this is a compare move operation. This is the only real branching operation. These go a maximum of 6 levels deep. So there might actually be some improvement to be had if we got rid of this branch. We could get rid of this branch. We could get rid of this branch by... Okay, I think we can get rid of this branch altogether. Well, we can't. We want to do it exactly 6 times. Okay. The idea here is basically I want to no, branch operations can get you in a lot of trouble. So, especially with a decision tree, like the way that decision trees are built, you almost pretty much evenly distribute yourself throughout the tree. And we're running a lot of trees the same time, and we're using the same. We're running a lot of trees at the same time, or for any given evaluation, we're running 1,000 trees, and we have the same loop going over the different parts. So the ones at the top of the tree are usually the most descriptive. And so it will send you down the same side almost always on the first one, but the remainder of them you pretty much split evenly. It's like the worst case scenario for branching. So getting rid of the branching altogether, I think, is going to have a fairly significant impact because these are decision trees. So the plan here is to eliminate this branch by running this as a for loop that runs exactly the amount of times that I want it to. Okay, the way that we're going to do this is we're going to say, we're going to pull this out, and we're going to say var should branch before I lose this. All right, so why is this giving me hell? Oh, okay. All right, so should branch, meaning I don't want to stop when we get to the index. Instead, what I want to do is make sure that the node index doesn't change. That's what I want to do. Instead of assigning node within the loop, would tracking just the index speed things up? Instead of assigning node within the loop, would tracking the index speed things up on line 41? Oh, you know what? I do have this available. Live share. I didn't want to do live share. I want to do this one. Twitch highlighter. All right, you can now use Twitch highlighter. If you're not familiar with how to use Twitch highlighter, you do bang line 41, and you see it highlights it like that. And then to undo it, you do bang line bang 41, and it will undo it. So now you can draw my attention to wherever it is that you want to draw my attention to. Okay, so instead of assigning node, just tracking the index, save node index instead of node equals node index. So if I save the node index, I still have to like index it repeatedly to get all of the values from it. So I don't think we're going to buy anything there. Oh, you're on the right path of what I'm hoping to do. What I am hoping to do is, yeah, basically to turn this into a for loop. So let's just do for int I equals 0, I less than 6, I plus plus. Why 6? That's the deepest these trees can go. And this is actually, this is a major. Let's just call it what it is. Hack. We know the trees cannot be deeper. This should be a parameter to instantiate by. Okay. And then the idea being line 41. And then the idea being that I say should branch. I want to say int false branch equals, aha, here we go. If it is not the leaf index, then node.falseBranch or node index. And then the idea, why is that failing? It's an int, isn't it? Oh, that's fair. Equals node.falseBranch. Okay. Actually, I can just put 0. Okay. Now I'm saying this is where I will go. I will always reset the node index in the case that it's a leaf. Because the value features. No, this isn't going to work either. let's just do it like this then. I'm not even sure that this is actually going to help at this point. So if it is a leaf index, which it almost always will be, more than half of the time, then we want to reset it to node index. Otherwise, we want to do this whole thing. And we don't need either of these. Okay, so this just resets it in the case, and we're always going to loop through 6 times. This takes care of this branch. This would be perfectly predicted after like the first couple of instances. This is bad. This is still a branch. I can't stop this. I really want to stop this branch. This is a branch because this has to happen. This has to happen before this. And the only way for it to do the move operation is to have the result of this. That's the trick. Do it backwards. In the case that this is a leaf index, it doesn't matter what the result of this is because it will always do this. And so even though this will be invalid, it won't matter. Okay, that's the trick of it. Okay, so now I want to say int non-leaf place. Okay. I think that is now branchless. I wish there was an easy way to get the code out of this. I wish there was an easy way to see what got compiled. This should absolutely be a conditional move. This should now absolutely be a conditional move, which is a single step. This will be basically a constant time because the same node will already be in cache, and this branch has been perfectly predicted. Okay, I think this might help. Not 100%. Lepersov, thank you so much for the follow. I really appreciate that. Hope you're having a great day. And let's see if this made any difference at all. We need to build. And then we need to run this crazy thing. And then we need to close all of this crap because none of it's useful. And we want to get rid of these two. I hate that it closes it when you do that. And then I want to run this. Index outside of the bounds of the array. Feature index is -1. Instead, I need to make that okay, so we're going to have to change the way the decision tree works. Let's just do maybe this will still work. Feature index and this. Okay. That seemed like it took longer. Yeah, that didn't help. Let's try it one more time. Nope. Okay. Okay. That did not help. Checking the same thing over and over. Yeah, okay. All right. Let's just do a little revert here. This is it. Yeah, that was a bad hack anyway. We'd have to pass that in. I'm really bad about actually committing things in the middle of the day. I like press Control S about every like 18 characters that I type, but as far as like popping in here and actually saving stuff, I'm really bad about it. No, we'll do that later. Should go ahead and take care of this. Okay. Oops. Gotta do this over here actually. On stage. On stage. I want to call this what are we saving this as? XG boost model correct. Control S. I often have a Word document version numbers over 100 and after 45. Yeah. Yeah. I'm just like constantly pressing those buttons. Okay. Let's see. Close all this stuff. Okay. New idea. New idea. We keep branching. So 6 times 1,000 is 6,000, whereas, yeah, I guess branching factor doesn't really cut down on it. Most of the time, you're not really going to get down to a leaf. You're going to get found out pretty early on because the class balance here is atrocious. The class balance is like 1 in 10,000. So it's not good. All right, what are we going to do to make this a little bit faster? How am I going to tell what the slow part is? This is like 99% of the work because the XGBoost stuff is literally just calling evaluate on each of the trees. This is all of the work. I'm going to have to probably pull this into Visual Studio to get the actual profiler on it. We're just so close. I feel like we ought to be able to figure it out. Maybe there's some improvement to be had by reordering the trees. If we take a look, well, I take that back because in the trees we see that they almost always link to 2 right after it. Okay. Can we take advantage of vectorized operations? by a value. These are all doing a less than. So could we pull in all of the features and run all of the non-leaf features at the same time? Unchecked? I'm fine with unchecked, man. Everything's on the table here. The only thing that matters is that I meet the performance requirements given to me. That's it. So just putting unchecked around the array access. Okay. So just here. That's what you're saying? Or up here? All right, let's give that a build. Let's give that a run. That seemed to be faster. 476. I don't think that made a difference. Let's try that one more time. Yeah, 476 and 476. Okay. Not a bad idea. I don't actually care. Like, we can guarantee that that's never going to fall outside of range. Can you do the whole function? Can I do, like... No. That would have been way too cool. That would have been way too cool. You could wrap your code lines in. Oh. Ah. Like such. Okay, let's give that a shot. I feel confident we can try that one more time. Four nine three. I feel like it's time to get kind of a better test harness. In any case, not an immediate and obvious change. Okay. Nodes 0. It could save ourselves the first node by going private decision tree node first, and then just saying first equal tree 0. That's actually not a terrible idea. Stuff first. Yeah, the Hugo doll, I think really honest, like you sort of have to run the things over and over and over and over and over again. I'm just running it like one time. Like a better test would be to run it like, to do the whole test thing like 10 times and then average it out. And that would give you a much more stable value. Like there's tons of stuff going on my computer. If it just happened that one time to run on the processor that OBS is running on, then yeah, it's gonna run into issues. Okay. There was when I first started working on Fast, I was working on this BLOS stuff and doing a matrix multiply with OBS running versus without OBS running was like a 50% difference in performance. It was just like unbelievable. It's like if you like the matrix multiplication was multi-threaded, so it was using all of them. So obviously it was gonna like interfere with the work that was doing. But on my box, you know, I've got I don't know, I have like 10 or 12 processors on here, logical processors, and 8 or 12. I don't know, whatever it is. If you just have a bad run and you end up on a processor that's being used by something else, you take a huge penalty. Yeah, benchmark.net is definitely one that I have heard of before. I am not familiar with using it, but I think it's probably time. I still feel like a 10% difference, like we're not at the point of like testing for micro differences here. We need a very huge chunk of time to be taken off, and I think a profiler that's showing me where everything is hung up would actually get me in the right direction a lot faster. First, let's just see if the first trick made any difference. $441. Okay, so that had a notable difference. That first lookup. Try that one more time just to be sure. 433. Yeah. Okay, so that was an improvement. That was an improvement. Are we really paying a penalty? Putting them that close together? Leaf index. Did I make leaf index a constant? Where the hell is leaf index? Okay, it is a constant. Okay, so that'll get replaced at compile time. Features. Feature index. This is pretty painful. This is actually quite large. This is 1,000 doubles. Okay, so this is 1,000 doubles, so times 8. So that's 8,000 bytes, and a page is 64 bytes, so there's 125 pages here. Okay, one thing that we could do is we could reorder. I'm going to guess that a lot of time is spent in memory lookup on this step. Reason being, like these nodes are all really close together because the array only has it's like 32. Okay, this is a few things. All right, first off, this is 4, 8, no, 4, 12, 16, 20. So each one of these is 20 bytes wide. So you can fit 3 of these in a page. The first 3 are always very close to each other. That's where you're landing most of the time off. Yeah, I'm going to guess that most of the time is spent in here. And what we can do is reorder the features. And by reordering the features, we can take advantage of paging on the features, right? Each one of these trees only has 33 possible nodes. And that means each one can only access like 32 features at a time. So if we made it so that any given tree always accesses basically the same block of memory, that could really, really, really improve things. So how would we go about reordering the features? We would take a look at the trees. We would find all of the feature indexes, and then we would group them by tree. And hopefully there's not a lot of overlap. Hopefully there's not a lot of overlap. Okay, let's try that. I'm just going to pop out on here for a second. All right, we're going to say, give me this file location. Code, culture of development, fast, datasets, XGBoost. All right, var file name equals at. So let's take not the test cases. I want the trees. So really what I want to do is browse. This is .NET Core. Please tell me that this is .NET Standard. Is this .NET Standard? Fast.modeling. Okay, net standard. All right, we ought to be able to include this. Browse. And I want to go to code, fast, modeling, bin, release, net standard. Okay. Additional namespace. I want fast.modeling, fast.modeling. Okay. So now I should basically be able to say this, and then I want to expose the nodes from the decision tree. Decision tree node, nodes. Okay, let's. Why are you complaining? What? I have a public class is less accessible. Oh yeah, sure, whatever. Whatever. I want to build this. I want to go back to here. I want to re-include this. Actually, that probably just did it. Then what I want to say is sort of the stuff that we had in the test here. To load it up. Okay. Then let's just say, let's just see if that runs. Okay, great, that runs. Okay, so now what I can do is I can take a look at the trees. I need to give them numbers. And what I want to do is I want to maximally order the features so that the same tree looks at consecutive features as often as possible. Okay? So model.trees dot select m dot nodes dot select j dot feature index dot to array dot dump. Nope, not quite. Okay. Model.trees dot select, and then let's do nodes dot select feature index to array dot dump. Okay, I think in here we can save ourselves a little bit of space. Okay, I want to do dot where j not equal -1 dot distinct. And I want to do distinct because you can see right here that this tree uses 732 3 times and 734 a couple other times, so we can actually save quite a bit here. And let's just save this to a thing, var feature uses. Dot to array. Feature uses dot dump. There we go. Okay, they all use feature 0. No, they don't all use feature 0. But most of them... Okay. Now I want to invert this. And I want to find the number of different trees that use each feature. Well, actually, first I want to just toss all the features we don't need. Right now we're using 1,000. And I think there's like a total of 800 features that go into the model at the training time, but the number of features that actually get used in the model, I'm totally unsure of. So let's say feature uses dot select mini m dot distinct dot count dot dump. Okay. Features used in the model. That one's actually pretty interesting. Let's just see what that is. There are 834 features used in the model. Okay. Split amongst 1,000 trees. So the way that we're going to do this is we're going to say features, and we want to invert this. We want to invert this. So what we're going to do is say feature uses dot select mini, and let's just m, and then we want feature uses m, and basically we want tuples of I and oh, I see. Okay, m dot select of, yeah, sure, x. What the crap is going on? And for this, I want x I. Okay, and what that will give me is 0 and 0, 17 and 0, 2 and 0, 6 and 0, and then 0 and 1, 17 and 1. And then that is grouped by m dot I dot x. We should just give these names. Tree index. X is not x. It is feature index. Tree index. Feature index. Tree index. M dot tree index. No, feature index dot to dot to dictionary m dot key m dot to array. So this will tell me, okay, var feature uses is a bad name here, wasn't it? Tree features. Feature trees. Okay. Now what I want is feature trees dot select m dot value dot count. Nope. New feature index. New feature index. I'm just really bad with naming. KVP feature index equals kvp dot key missing close on 19. Yes, thank you for that. I'm sorry I didn't look at the chat until just now, but thank you so much for that. And then I want to count tree count equals kvp dot value dot count dot length. select. Okay. And we can cut off. Oh man, these are used a freaking ton. I was sort of hoping that there would be a lot of not so much overlap. Okay, so this was like an optimization problem at this point, right? You have a bunch of things that have a references to a bunch of other things, and you need to use the fewest number of pages per thing. You can fit 8 doubles. Am I thinking about this right? Yes. You can fit 8 doubles in a single page. You want to minimize the number of pages needed on average. So right now, the way that they are ordered, we can sort of figure out how many pages there are being referenced, and then we can sort of try to drop that down. Okay, so if we have, all right, we're going to comment this out, and we're going to have this thing called a, let me just close this. So we're going to have this function, private, I don't actually need that, double or int page count, and this takes in an int array of feature indices. And then what we want to say is feature indices dot select, and then we want to say m minus m mod 8 remainder 8, and then what this will do is drop it down, basically latching it to the closest value before it. And then we want to say distinct, and then we want to say count. Return. All right, this is a rough estimate of the number of pages. Just so we're clear on how this works, if we had the value 0 and we had the value 5, 0 minus m remainder 8, 0 remainder 8 would be 0. So 0 minus 0 here would be 0. Then if we had 5, we would have 5 minus 5 remainder 8 is 5. So this would also latch to 0. But if we had a 10 in here, 10 remainder 8 is 2, so this would latch to page 2. So we're basically saying this value is at this page of memory, and we're counting up the number of distinct pages. Then what we want to do is we want to say int perf metric, and this needs to take in a, what do we have this as? An array of arrays? Tree features. Yeah, sure. An array of arrays. Of ints. Is that right? yeah, int array of tree features. And then we want to say basically return tree features dot average. I don't really like this autocomplete snippet. Tree features dot average. I think we can just say page count. What does it not like about that? Oh yeah, this needs to be a double. And let's just make this a double. And let's make this a double. Okay. All right, so now we have a way to estimate the total number of pages of memory that have to be accessed, just period, in order to get through this. Okay, so let's just say perf metric of tree features dot dump. Wow, 19 pages of memory on average. That is atrocious. Considering how is that even possible? It's not. Okay, this is a bad. Okay. It's not possible. Half of the nodes have to be leaves. How do we have more than that? Give me tree features dot dump. Tree features. That one has 12, that one has 10, that one has 14, that one has 13, 23. How do you get 23? What is this? 1, 2, 3, 4, 5. 5 uses 23 features. I find that difficult to believe. Let me just clean this up real fast. Go to datasets, go to trees, and we want control F booster 5. One, two. How big is this tree? Oh, look at that shit. There's 38. Huh, that's totally interesting. Okay, that's sort of unexpected. F0, 2, 27, 732, 738, 655, 734, 763, 722. $790, 629, 421, 284. I only got 13. Am I missing something? Oh, yes, I am. It's this one. Oh, and look at that. Okay, 56. I am. It's zero indexed. Okay, yeah. No, this one. All right. This one has 56 nodes. Wow. That's incredible. It's incredible. So you won't actually access this many. You have a maximum of 6 that you will access. And the reason for that is because the tree only goes 6 levels deep. So I would be super interested to know based on any given path through the tree. Okay, so based on any given path through the tree, how many different pages would you hit? That's what we need to optimize for. Which basically means expanding all possible paths and then weighting them by how often you would expect to go down that path. Because you're not going to go down every path equally. There are a lot of trees up here at the top where, like, this is the most important feature, and it leads directly to a leaf. I don't know how to estimate. Okay, so, all right, so actually we do know how to estimate. Roughly 27,584. So you just take this divided by this. So you take the parent, and that's the percentage of the time that you would expect to go down that path. So now I can calculate all possible paths through all trees. There are at most 64 paths through any tree, so 64,000 of these things is not an incredibly difficult thing to calculate. And then we could weight it by how expensive it is to go down that path. How many pages on average you would have to load to go down that path. Okay, let's take a look at that. That's a much better way to go about this. I'm going to shrink this a little bit so we can get a little more on the screen. And I'm going to close this. So the perf metric is now feature indices. I actually need the trees themselves. I need the trees themselves. Rhyolite, thank you so much for the follow. I really appreciate it. I hope you're having a great day. Okay, so what we want to do is we want to take a look at expanding all the trees, all the possible paths through a tree. What is that? Oh, that's funny. Little brain. I need to get around to actually making some emotes. That's like the thing that I have been wasting. You know what I am? I'm gonna take a little brain break for a minute. But I've not gotten around to actually making the emotes for my channel yet. I just started working on like getting a little bit of the actual design of it going, a little bit of the chrome here and there. but I haven't spent the time to sit down and actually make it look like I want it to look like. Hardly anyone during neural nets on Twitch. This isn't a neural network. This is decision trees, and right now what I'm trying to do is improve the performance of it. I don't know how long you've been here, so I'll just cover it one more time real fast. Basically, what happens is I am a data engineer. I am not a data scientist. I collect a bunch of data. I give it to my data scientist. They make a model. They give me the model. It's now my job to make this model run in production. So the first thing we looked at was, hey, can I just use the tools that you built it in and see if we can make it run? And the answer to that turned out to be no, because for any job and user combo, it was taking the API that this thing had like upwards of, I don't know, it was like 100 milliseconds to do an individual job, anywhere between like 10 to 100 milliseconds to evaluate like a single job user combo. We need to be able to do 10,000 of these in under 50 milliseconds. And 50 milliseconds is like a hard cutoff. Like, just period. I have to do all of this work and send back the results in less time than that. So, like, with the network overhead and everything else, ideally we would want to get this done in like 45 milliseconds. Any less than that would be even better. So the 10,000 literally was taking it like minutes to do 10,000 using the R API. So instead we said, okay, let's write it in C sharp, see if we can make it faster. It turned out that like the way that it works, the prediction method works in the R library was just really, really awful, and it was doing all of this conversion between like the R data format and the data format for C++ that was actually doing the prediction under the hood. And it was like going back and forth with this multiple times to do a prediction, which is why it was so slow. So instead, we're doing it in C sharp now. In C sharp, we're going to see how much better we can do this. And on the very first try, like with the like crappiest, no effort put into it whatsoever, we got it to about 1,400 milliseconds to do 10,000. So about 1.5 seconds, which is still, you know, orders of magnitude off. But it wasn't the end of the world. It was need maybe a 30x speed up. That was running in debug mode. When we switched over to production mode, it dropped down significantly, and then we saved a lot more time by when we started compiling it in release config. Yeah, we had a huge perf boost. Then the next thing that we did was we changed this internal node structure from a class to a struct, which made this a lot more efficient because it will assign a bunch of memory next to each other instead of creating references. And then the last thing that we did was we took the first node for the decision tree, which we always have to go look for, and we just assigned it to a variable. So instead of doing an additional array lookup, we eliminate that altogether. And that actually took out quite a bit of the time. Now the part that we're trying to optimize is this part right here, which is this feature lookup. This feature lookup is a very long array of basically doubles. And what we need to do is reorder the features so that for any given path through a tree, we're minimizing the number of pages that we'll have to look at on average across all of the trees. And so we now have a little optimization problem that we're trying to solve. And so the first thing that I'm doing is creating a metric to test how good we are in terms of number of pages that we have to visit. And the first attempt at that was just awful, the way that I went about it. This was about the only valuable step out of the whole thing, which is that it counts the number of pages, but it was counting the number of pages for an entire tree. And that's not what we need. We only really care about the number of paths that we can possibly go through these trees, and these trees are a maximum of 6 levels deep. And so when we ran this the first time and it was like, hey, you have a 19 page average, that's just obviously not true because you can only look at 6 pages for any given evaluation. So what we want to do is we want to run every possible path through these decision trees. There's at most 64 paths through any one of them. So it's not going to be like incredibly difficult to do that for 1,000 trees. And then we should be good. You know, another way to like really improve this is probably just cut the number of trees in half, and I bet you we would save 50% of the performance right there, which would get us really close to where we need to be. Like extremely close. But I like the feature ordering better anyway, so let's work on that still. I wonder how much performance gain in terms of like predictive accuracy you would lose by throwing away half your trees. It's a boosting model, so I really don't know. I really don't know. I might go back to the data scientists and ask them to check that out. Okay. But in the meantime, we need to expand every possible path through the tree. We need to calculate the percentage of the time that we will go down this path. And we need to calculate the total number of pages of memory that you would have to look at in order to go that path. And that's what we're going to do. And then I think after that, I'm going to start wrapping things up. Once we get to a number where like we can look at this and think to ourselves, okay, great, this makes sense. We need to minimize this number as much as possible. We then have an optimization problem. We can go and solve the optimization problem. And then the only thing we're going to have to do after that is figure out the feature mapping. Yep. Okay. That's fine. Okay, so let's do void expand all paths. Expand all paths. How do I want to do this? Basically, you are given a node. Okay. Where... No. Yeah. Trees. Dot trees 0 dot nodes. Okay, so I need a decision tree is what I need. Decision tree. And the results of this should be path weights. Yeah. Basically a list. Okay. Var path page weights equals new list of doubles. Return path page weights. Okay, and this is going to be a list of doubles. And what we're going to do for the perf metric is we're going to say, oh, you know what? We're going to actually just leave that there. No, we're going to delete all this because this is garbage. What we're going to do is we're going to say decision tree array trees. And I don't really want to do that either. I want to say XGBoost. XGBoost trees. Model. Whatever. And then I want to say model dot select mini m dot tree. I hate it when it does this. Why is it complaining? Oh, great. Oh, yeah, model dot trees dot select many m dot nodes. No. Expand all paths. Dot average. Okay. So this says for each tree in the model, give me all of the paths and then make a giant flat array out of all of those and then just give me the average. Okay. So much for stepping away for a bit and working on stream emotes and such. Oh, yeah. Well, no, I'm not actually going to work on that on stream. I don't even know what to do for it, though. I've been thinking, like, I want to have this, like, left brain, right brain theme, right? First off, I got to flip this thing upside down because the left brain is, like, the analytical brain, and then the right brain is the creative brain. So I want to flip this logo upside down altogether, which is going to be kind of a nightmare because it's all over my website, too. You go to, like, actually, let's pull out something like, yeah, right here, because I got to change it everywhere. I can't just change it in one place. And then when you sign up, when you like subscribe, you get like a tier 1, a tier 2, and a tier 3, and I'm not sure how to like organize the theme to make it, you know, better and better. And then you also have more emotes for like if people have donated you bits, and as they donate you more and more bits, they get different designs as well. I'm not entirely sure. I just don't know. Like my theme is very like AI brain related. I can't think of exactly what I want the rest of it to be like. I do know that like I've got over here, you know, where is my mouse? What are y'all looking at? Yeah, like it's like you can't even see my mouse. Oh, weird. Anyway, over here where this stuff is right now, I want to move that down into this bottom bar. And in the bottom bar, like just get it off of the screen, basically. A Ricky Bobby. I want to go fast. Oh yeah, it's not a bad one. I like that. I'm gonna put that down. That's awesome. Put that in my show notes real fast. To do. Do the XG boost. Do the perf tuning. Consider Ricky Bobby. I want to go fast. Emote. Yeah. That's a great one. That's a really good one. Thank you so much. Let's give you a little credit here. The Hugo doll. That is awesome. I want to go fast. I want to go fast. Yeah. Okay. That was a good one. Yeah, I have like moments of inspiration where I can actually like sit down and think of stuff like this, and it just comes flowing out. And then usually I'm just fine with it later. But I think I just like way overthought this and put way too much effort into it instead of just like taking the really like simple high level approach to it and just it doesn't matter. It's just an emote. I'm just building content. Okay. Oh, and now my wife's reaching out, which means probably gonna have to wrap this up soon. Okay, so I am gonna save. I am just gonna stop. It's 3:30. I have been up here for about 3 hours, which I think is a pretty good run for today. We're pretty sure that this is the problem. I'm gonna have to get it out of VS Code because I don't know of any good. I don't know of any good profiler on like a line by line level that operates in VS Code or on the command line for that matter. But there are a number of tools built into Visual Studio to do profiling on code exactly like this. So if we get this organization, before I waste all this effort on the organization, I should probably just verify that this actual step is what the problem is. So I'm going to have to break this up into a couple of different lines. And then we'll test that out, make sure that that is actually the slow part. If this does turn out to be the slow part, then yeah, this organization thing and solving this optimization problem is probably going to prove to be beneficial. And then outside of this, I don't think I'm going to have too much trouble going back to my data scientist and being like, hey, look, instead of 1,000 trees, let's just use 500 and seeing what the results are if we do it like that in terms of the predictive value of what we're trying to solve here. If it turns out to be basically the same, then yeah, that's just free perf by doing less work. Okay. All right, so that's it. Tomorrow, that's what we're going to do. We're going to verify that this is actually the problem. That'll be the first thing that we do. And then the second thing that we're going to do, hopefully, is the optimization problem because there's just not a whole lot. I mean, we sort of ruled out the idea that the branching was the issue, which to me in my head means that most of these trees end way before they get to the bottom of like a full binary tree. So they're not running a full 6 levels deep. They're really only running a couple of levels deep. Right? Yeah. Do the perf tuning. Well, okay. This is actually done today. And that was actually done today. So let's put that on the done list. 2019-05-23. I don't actually. Okay. And then do the work to verify the perf black hole. Do the work to fix the perf black hole. Okay. All right, perfect. And watch me check it in. If anybody wants to grab this and mess around with it, this is posted on my GitHub, which you can find at Bang GitHub. By all means, well, it's not the JS13K, it's actually the fast one. So if you go to GitHub, github.com, and then you go here, this is actually the one if you want to go play around with this stuff. There's a number of projects in here. This is all in .NET Core. And the one that we're working on right now is fast.modeling. And fast.modeling is super simple because it's the only thing in here. Inside fast.datasets is the dataset for XGBoost that you actually need. Oh, crap. And I left the art history in there. That's awesome. Whatever. That's fine. I didn't put any feature names in there. Okay, but yeah, these are the two files that you'll need in order to. One of these is the definition of the trees, and one of these is the test cases uh, for running the test. But yeah, let's go ahead and check this in. To do. Decision tree. And I want to say perf work on decision tree. Commit. Okay. And push. I use a GUI, by the way, for all of my Git interaction. Hey, that would be cool. Yeah, if you want to take a look at it. Yeah, it should honestly be as easy as like breaking this out into a bunch of lines. Like, get features var thing equals features. Oops, we'll just call it F. Right, now you can know if it actually gets sucked into this line. Another thing that you could do is actually well, you can't turn this into an if statement or you'll lose this. You have to keep this as a ternary, or else this is guaranteed to turn into a branch, like a for real branch. And then maybe this one needs improvement as well. I'm very, very suspicious of this line. But yeah. How can you focus on performance and use a GUI? Man, it's about things that you commit to memory. I don't commit anything from Git to memory. I know it's just one of those things that would really improve my life if I did. I just, like, for some reason, I just can't help it. I always look up anytime I need to do anything in Git, so I don't worry about it. And I like GUIs. They're good for everything. Yeah, I'll believe this. There are ways to make this faster. We could reorganize the way that this is stored entirely and not do it as a structure. And then we could focus on getting better paging. Because it's possible, since this is 20, like if we just expanded this with some features, no, then we would guarantee that everyone's like, yeah, I don't really know. Or because these branches are only values up to oh, this is another one. We could just do this. We could just change these to bytes. If we change these to bytes, you now have 4, 8, or 4, 12, 13, 14. Could even make them shorts. And then we could fit more than one of these tree nodes. We could fit a lot of these tree nodes, actually. We could fit 4 tree nodes in a single page. God, that might actually make a difference. Because right now it was 20 having them as ints, which wraps them. There's a lot of things we can do. Yeah, there's a lot of things we can do. God, I just want to try that now. Of course, I have to change the way that we instantiate these to do short. Let's just give that a shot real fast. I'm gonna laugh if this is just like, hey, it works all of a sudden. All of your wildest dreams have come true. Fast up modeling. No. Not an improvement. Maybe on the second try? Did I save the file? Okay, yeah, 445. So I feel, yeah, that didn't make as big of a difference. Okay, yeah, there's lots of stuff here to like look at. But overall, I think we're definitely going to get where we're trying to get with this. And it's great because right now all of this is like single threaded as well, which is going to make it so that we can run it basically anywhere. Another huge benefit here, like we're not going to have to worry about parallelization or anything. So yeah, lots of cool stuff going on here. Anyway, I'm gonna get going. I'm like way over, but thanks everybody for hanging out, and I will see y'all tomorrow. I stream normally on Wednesday, Thursday, and Friday, starting at noon, and I go until like 2 or whenever I decide to quit. Let's go ahead and raid somebody. If anybody has suggestions, Code Rush, thank you so much for the follow. If anybody has any suggestions for who you'd like to raid, by all means, feel free to send me your suggestions. And I am currently going to look for somebody. Oh, the Michael Jolly. Yeah, let's go with the Michael Jolly. There we go. The Michael Jolly. All right, here we go. All right, again, thanks everybody. And I don't have anything to spam when you get there, but say hi and just pop your head in there and say what's up. And yeah, hopefully I get to see all y'all tomorrow.